grade? Okay, so I keep saying that we're going to be doing this car building project soon, where you have to create, the only way you can make it move is through balloon power. So that is for next week. That's like the big thing. That's what you're going to be working on. Before you can start that, you got to learn a little bit more about this whole motion and work and power thing. So this week, we're going to be focusing on what does the word work mean, in particular related to motion and everything. Power. So how's that related? How much you need to power and put the work in for your car to actually move. And then I'm going to quickly go over the different types of simple machines that can help you think about how to develop your car. Now here's the thing. Next week, you're going to be building your car, but on Thursday, Friday of next week, you'll have a mini quiz, but I'm going to throw up there, these are your challenges, the ways you have to test your car. And you're going to actually test the car and record how far it goes and everything. And we're going to see who has the most successful car. It's going to be interesting because we're not in the classroom doing this, but you're going to be on the honor system for the whole thing. But it will be fun developing it. So a whole week just to build this thing and test it out and then share back what you got out of it. And like, hopefully there's a winner. And if there's a winner chicken dinner, I might have a big prize for you the next week. So let's get started. And I apologize, this might be another 20-minute video, but I'm going to move really fast because I'm actually recording this on Easter, and we're supposed to be egg hunting in a little bit here. So welcome to the life of a teacher and yourself. Okay, so we're first going to start off with one of your vocabulary words, work, okay? So you're probably thinking, like, going to work? No, this has nothing to do with, like, going to work. But work means to actually apply something. So write this down. It means to apply force. Remember, force is the change in motion, okay? So there has to be some kind of force implied, put onto the object. So if that's gravity, friction, acceleration, whatever it is, something has to make the object move. So that's one reason why we're moving these cars. Applied force makes object, I put OBJ for object, move in, quote, same direction. All right, so I'm going to underline same direction because the work is making it actually move. So if you have to push a box from one end of the room to another, that's work. Is you pushing the box in one direction to go that way. You're putting the work in. You're applying force. Push is the force in order to get it to move. There's a lot, like I said, there's a lot of forces at place, but you have to actually, to make the motion happen, put the force in, make the work, we have to actually apply it. Okay? Same in direction as applied force. And I'm going to get a different color here. The formula for work is work equals force times distance. Now, we've been working on some formulas here over the last couple weeks. In 2 weeks after next week we're doing the cars, and then in 2 weeks we're going to actually learn how to calculate the force and the speed. You've already worked on speed. So we're going to actually start mapping it and graphing it. So we're going to bring in a little math, but it shouldn't be too bad. So here's your definition for work. Applied force makes object move in the same direction as applied force. So push, I'm going left. If I'm going straight, that means that the work is that the direction is going to go in the same way I'm going. The way you formulate it, calculate it, is work equals force times distance. So how much force you put in times the distance. So if it's 3 feet times 15 miles an hour kind of thing, then we put the work in. So that's a random example for you guys. Now, on top of work is power. How much, almost like effort is probably the best way to put it. So I'm going to write down power. Okay, this helps us. It's the rate at, I'm going to use the at symbol, rate at which work is done. Okay. Power. Rate. Okay, so calculation at which work is done. So this is the power is the calculation that we were just working on for work. Okay. You with me? The eyebrow thing. There's a little bit more that goes with this. So to break it down, if you're kind of like, huh, I still don't get it. It's how quickly or slowly the work is done. So if you're like me, who's constantly like, we got to get the work done, I'm probably moving pretty quickly and pushing that box across the room. Now, when you are trying to ask Jonah, who is still in kindergarten, and he has cars on his mind or whatever, and I'm saying, I need your help because I have to push this box. I need you to push that box. I probably will move like 4 boxes compared to his 1 box. So my power is much greater, it's much quicker than his power at that point. So I'm sure all of us have siblings or somebody in your house that you're doing the work 10 times faster than them and they barely have picked up the mop or something to help you. I don't know. It's just the way our motivation and everything, but there's actually a science behind it. I mean, power. Isn't that crazy? So that nagging and everything you do, like, why didn't you clean this yet? It's mentioned I could have done that. Let it go and just say, it's because I got more power going in, pretty much. To go with that, let me add a little bit more here. More powerful machines, just like I just said, more powerful machines perform work faster. Write that down. So it's like, wait a minute, didn't I just say this? Yes, we want to actually write that down. More powerful machine. The more powerful the machine, the work's going to move a lot faster. So you could put together quite a few simple machines and your work could get a lot faster in the power because if you put together a couple of simple machines, the power will increase, which makes the work go a lot faster. Theories, huh? So, I mean, having Jonah help me move, if he moves even just 1 box, my machine, even though it's not a simple machine, we're pushing across the room, but he's still making, by adding him on and doing the work, we're getting it done quicker. Even if he's not moving at my pace, it's still more powerful. Calculation. P is power equals work divided by time. So you have to figure out the work from the last formula, put that answer here, and then we divide it out by time. And that gives us how much work, how much effort is being put in per time in minutes. So it's really cool how you can calculate all this. Now, with that knowledge behind you, you want to keep that in mind for when you're building your car. Because we're going to go into the simple machines, because there's going to be some challenges. Like I might say, put an inclined ramp at 24 inches, highest point, and everything. So you have to think about putting that balloon on that car as your only power. How do you get the car to become a powerful machine to actually use that force to use the force that's using a power balloon to take advantage of an inclined plane to move it as far as you can. Crazy, huh? So this is what we call a trial and error on this thing, for sure. It's not going to be you're going to do it once and it's going to be like, this is done, I'm amazing. No. Simple machines, let's get into them. Okay, so what is a simple machine? That might help if we actually define that. The last time you probably have talked about simple machines might have been years ago in elementary. But that's why we've been building. Simple machines, this is what's great about them. They make the work that we were talking about at the very beginning easier. That's all it is. So one little adjustment, like I could have created a pulley system that I could have attached the boxes to, right? And then I press a button and then that pulley system takes those boxes across and the pulley system comes back. So I go over there, come back. I don't have to put that much work in. Jonah would have figured it out, pushing those boxes, and it would have made our work a lot faster. Simple machines. Crazy, right? And it's like, what else goes with it? So that's it. Okay, so there are quite a few of them, so we're going to get started on that. First one is, these first two technically are the same things. First one is a ramp. And these are vocabulary words that I'm popping out here. It's an example of a machine, but what it does is it helps decrease, as I write down, helps decrease the amounts of force. Remember, gravity is pushing down, and how force is like what you have to, the effort you have to put in, the power you have to put in. Helps decrease the amount of force, sorry, I lost my track, required to do the same amount of work by increasing the distance. Basically, the simple machines makes it where you can do the work. I'm about ready to get this ready for you. With a single motion. Boop. Okay, there we go. All right, so ramp. All right, now here's the crazy part. Let me read this. Helps decrease amount of force required to do the same amount of work by increasing the distance. So a ramp is basically, we're not talking about how high it is. The ramp is how long it is. So if I tell you to make a ramp that's 24 inches high, you can decide how long that ramp is. The longer the ramp, the better the force is going to be, the better the work, the less work you have to put in. If you've noticed, people who are in wheelchairs, some of those ramps are stinking long. Like, they're really long. You're like, this is such a waste of time and everything. The reason why is because it's putting less force on that person who has to do it. By increasing a little at a time, they're able to put less effort into going up. It may take longer. It may, which it probably will. But there's a reason that we have developed this science in order to help people out. Now, if you just develop a ramp that just goes whoop, you're putting a lot more effort because it's shorter and it's taller. And yeah, you can roll up whatever you need to in order to get into the house, but there's a lot of time and management effort. And if you're like a 99 years old and you're trying to go up that thing, you're going to need something that's going to make it a lot easier. So keep that in mind when you're building for your car. Now, related to this is also, a ramp is also known as an inclined plane. Plane is like, not the plane that flies. Plane is like, you want to think planes like the ecosystem, where it's just flat, okay? So it's a flat line that goes up. This one reduces, there's a key word in here, reduces amount of effort. You want to circle the word effort, which I'm doing right now, and required by increased distance. So it's exactly like the ramp, okay, but for an inclined plane. Now we're putting these two words together, inclined plane and ramp, but now we're focusing on, it has to do with the effort. So when it comes to the 99-year-old man trying to wheel himself up that ramp, they're making it, whoever's the designer, engineer, they're making it where there's less effort that has to be put in to getting up that ramp. Bam. Yeah, it's making sense, isn't it? Okay, so that's two of your simple machines. The next one is wedge. Try to speed up for you guys, because this is going to be a long video. Bye, Mr. Greenwald. Wedge. Okay, so a wedge is a movable incline plane, and it reduces, a lot of these guys, it just reduces the effort, reduces work, right? To split or lift object. OBJ, object. So this is your definition for wedge, okay? So it's a movable incline. So it's still like that shape that where incline is, but this one we can actually move. We can take from one place to another. So it's like a knife, an axe. Doorsteps, plows, different things like that. But all it does is it's still reducing the work, the effort that we have to require to make that object move. So another one, inclined plane, wedge. The next one is a screw. Never would have thought that was a simple machine. But the cool thing about a screw is that it makes it a lot easier to get something to hang up in the wall versus putting a nail through it. Nail just goes straight in, but a screw, if you're tightening it as you're putting it into the wall, it's creating less effort for you to actually have to hang that picture up. Screw is another wedge that's wrapped around a post. So post, and then it's just swirl around it. I'm sure a lot of you guys have probably seen screws and everything. Now the big thing with a screw is that it's because by having that swirl around it, it's lengthening out versus a nail. It's very skinny, right? A screw is a longer inclined plane, okay? So it's in another wedge. By having that longer distance, it's making less effort for us to have to put something into the wall or to put a screw into a piece of wood and everything. So crazy, because you're still having to use some muscles in order to get into some of that, but it helps to dig in versus a nail. It might be a little harder. Your next simple machine is a lever. Okay. A lever reduces effort required to lift. Now, the thing that goes with this one is that there's a word called fulcrum. Sounds like something from Avengers. The fulcrum is the pivot point. Okay, pivot point means where it's the middle. So if you have a seesaw, okay, you're going to put your pivot point kind of in the middle. But here's the thing. It goes up and down. Okay. Now, if you are trying to lift Dad, on the seesaw, here's the thing. If Dad moves closer to the pivot point, the fulcrum, then it's easier for you to move him. Yeah, seriously, that's what a lever is. It reduces the effort to lift. So if you focus on that, if the mass object is closer to the fulcrum, then it's easier to lift. There's tons of different ways you can do a lever. As you can see in this book, see, this is the one I was just going with. Here's another fulcrum one. You can put those wheels out here, so then it's easier for you to lift. The further out they are, or closer they are to the mass you're trying to lift, it's easier to do. And even here, when you're trying to lift this, your fulcrum is right here. How you position yourself to lift something. Pretty cool, huh? So that's what a lever is. It's like, and a lever even is this switch that makes it a lot easier to move something. Now, we are almost done, which is awesome. I know there's a lot of simple machines. In the classroom, we probably would have built these, and you guys would have really would have experimented with them. Wheel and axle makes me think of a caveman. I don't know why, but a wheel and axle is just two wheels attached at an axle. It helps move the distance. I'm going to go ahead and add the last one. It's a pulley. You guys probably already know what a pulley is, but still, pulleys. It's a wheel with rope wrapped around it. And I'll show you some pictures here to really help you out. Ta-da! All right, there's your last of your notes. Wheel and axle, 2 wheels attached to an axle. Pulley is a wheel with rope wrapped around it. So it's like kind of thinking, well, what does that mean, Mrs. Greenwald, and everything. Here are some examples, guys. Okay, so I love this book. When it comes to wheel and axle, here's an example. Here's one wheel, and then here's the axle. Yeah. Okay, so here's the easiest one. A wheel and an axle, like a car. This one has 2 wheels. So you got this wheel, and they act together, and this is the axle to make it work. Here we got 2 wheels. One wheel here where you're pedaling, another wheel, and the axle is connected. So this wheel powers this wheel and just keeps going. Simple machine. If I power this one, then it's going to move that one. It's a lot of like gears in a clock. Pulley. Right there. This is the best one to use if you're trying to lift like a cow or something. So instead of you trying to physically lift it, you can attach this rope to the cow, and then you pull the rope, and then magic happens. It's a simple machine. It's all because you're putting less effort in by using a simple machine. Now, if you put the simple machines together, then they help with the workforce and the efficiency to make it work better. So your car can have a couple of different simple machines added to it, or you can just keep it simple. Anyway, so that's our notes for this week. Sorry it was a little longer than it usually is. What do you do for your experiment? Have fun. Experiment with different ways to move a lion. So I have loaded up a website, and you guys go get a little cartoon figure, something, a little animal, and then figure out different ways to move it by using these simple machines. The website tells you exactly different ways to do it. So I want you experimenting with this. What's my homework for the week? Not my homework, your homework. This is what you're going to do. You're going to go on a scavenger hunt around your house. The document is saved as Simple Machines Around Home, 6th grade. But on when you print it off, it's actually going to say around school. No, I don't remember. Anyway, so what you're going to do is you're going to list examples of, like, if you're going to go around trying to find, like, a lever and pulley. No, you're going to go around trying to find a pulley example around your house. So what you're going to do is you're going to write it down what it is, draw a picture, and explain how that particular example is a pulley. So we are actually applying it to real life. How do you actually see it? You'll be really surprised how what you find around your house. Use your parents to actually help you with this scavenger hunt. You're going to have a lot of fun. There's enrichment activities too. Vocabulary is already up there. There's a couple because of all of the simple machines. So let me break it down. Vocabulary for the week. Take your notes for the week because there will be a quiz coming up. And experiment with the different ways to do the simple machines. Go scavenger hunting for yours. That's it. That's all I got. Next week's going to be a lot shorter video for you guys, and because we're building our cards. So start brainstorming and having fun with it. Bye.